All right, so we were talking chapter 11, and we are talking about really getting into sort of the last part here of chapter 11, which is electron configuration. And as we talked about, we moved away from Bohr's model of sort of the planetary model of the atom, where electrons are moving in these orbits, to this more sort of wave mechanical model where we don't know exactly how a particle like an electron is moving at any given point in time. We don't know exactly where it's located at any given point in time. The best thing that we could do is, again, come up with this like probability of around this location, maybe there's a higher probability of finding an electron, again, not knowing exactly how it's moving or its exact location, than maybe further away from the nucleus. And again, around that nucleus, because of its positive charge, there should be a pretty higher probability to find those negatively charged electrons somewhere in that area around it. Again, also thinking about what Heisenberg and de Broglie and all those guys said, that basically a particle like an electron can have wave type functions. So it's sort of tied to the nucleus and is moving around in sort of a wave like function as well. So we talked about where these electrons are located, and again, they are located in what are referred to as orbitals. And again, these are also specifically what are known as atomic orbitals. And again, we don't talk about electrons in orbits because, again, they're in that empty space. And that's sort of where you would find these sort of orbitals if you want, in that empty space where the electrons are traveling in the atom. Again, these are based on sort of probability maps. You're not going to probably find these shapes and stuff in the atom. It's just sort of theoretical calculations of high probabilities and low probabilities of where you can find electrons. But remember, as we talked about, any individual orbital, and if we represent that again with a line, could hold a maximum of 2 electrons, if again each of those arrows are representing an electron each. Now, we saw that on different energy levels, we start to see these different orbitals start to first appear. And on that very first energy level, which is the lowest in energy, closest to the nucleus, there really is only s orbitals basically there present, or an s orbital only present. And as we talked about, there's only one type of s orbital, which means it would max out at 2 electrons if you filled it. There are s orbitals on every single energy level after n equals 1 as well. When you get to the second energy level, as we talked about, that is where we first start to see p orbitals appear. And p orbitals, there's 3 different types. That was the kind of X, Y, and Z. And as we saw in those little animations, they're on the x-axis, the y, and it's a 3-dimensional space. And because there's more than one, unlike an s orbital, like a 1s orbital, there are 3 different types of p orbitals on any energy level. Each one could hold 2 electrons, which means if you were to max out, as we talked about, what is referred to as the subshell or sublevel, you can max out at 6 electrons. And that would be putting 2 electrons into each of the different p orbitals on that particular energy level. Again, p orbitals do not appear until you get to the second energy level. They then appear at all other energy levels after that. So again, if you go to n equals 3, n equals 4, n equals 5, and so forth, you will find p orbitals on there. The number in front just changes as you go to the different energy levels. So if you're on the third energy level, they're referred to as 3p orbitals. If you're on the fourth energy level, they're referred to as 4p orbitals, and so forth. So again, as we talked about, kind of that, like we see here, 1s, that number that comes before the orbital sort of letter represents the energy level at which you are on in terms of those orbitals. Now, if you get to the third energy level, that's where we start to first see d orbitals appear. And there are 5 types of d orbitals. And remember, those are the ones that kind of look like 2p orbitals stuck together. And, or a clover leaf, I think is how they described it. And because there are 5 different d orbitals on any energy level where there's a d, and you can put 2 in each, and if you fill them all up completely, That means if you filled up the entire D subshell, that's going to get you 10 maximum electrons that would be filled. Again, 2 in each of the individual d orbitals. Lastly, on the fourth energy level, that is where we first start to see f orbitals appear. And there are 7 types of f orbitals. And again, 1, 2, 3, 4, 5, 6, 7. Each of these f orbitals could hold 2 electrons. So once again, if we filled up the entire f subshell on any energy level, you can max that thing out with 7, not 7, bad math there. 7 times 2 is 14 electrons to fill the subshell. Now, in terms of f orbitals, honestly, you only see them on the 4th and 5th level is the only time you'll come across them. Even with the D will really you'll only come across based on the periodic table and how many elements we have. You only have D orbitals that run basically from 3rd energy level to 6th energy level, and they really won't go to the 7th and stuff like that unless they start inventing more elements. So, in terms of what we typically use in terms of these orbitals, S's on all energy levels 1 through 7, P's 2 through 7. D's, we have energy levels basically a 3 through 6, and F's typically we use 4 through 5. That doesn't mean you couldn't, in theory, have F orbitals on like the 6 energy level and 7. We just don't use them because there's no elements available to do so. These are really the 4 orbitals that you'll deal with in pretty much all your chemistry classes. They technically go after F. They go just alphabetical, G and so forth, but we don't ever get to them because of the elements that we currently know of. They don't get any past F orbitals and stuff like that. But in theory, based on all the math that all this is based off of, in theory and the quantum numbers, you actually could go past F and it just kind of goes alphabetical on that, but we don't use it for anything like that. Any questions on that there? Yeah. Yeah. That is correct. So hydrogen, because it only has one total electron, we fill these from lowest energy to highest. So it would have just one electron hanging out in that one s orbital, and that's it. So all these orbitals and all these subshells, they don't necessarily always have to fill up. They can be partially filled. They can fill up, and they can be anywhere in between. So example like the F subshell there, you might come across an element that maybe only fills a couple of those orbitals in there, and the rest are empty. Or you may have some elements that don't even get to those sort of subshells, and they're just empty and stuff like that. So you don't have to fill them up completely. We're going to talk about how they get filled in the orbitals in just a bit and how the electron configuration actually goes. But to answer your question, yeah, so hydrogen, because it has one, starts on the bottom. And all elements start at the bottom. They start at that first energy level at lowest and just keep building up. And they fill up lowest energy to highest in terms of the orbitals. All right, so it's supposed to talk about sort of that energy of the orbitals. And as we sort of were looking at, this is sort of the arrangement here. And a couple of terminologies that we did talk about why we have it here. This obviously would be n equals 1 on the bottom, n equals 2, n equals 3, n equals 4. And again, those n is the principal quantum number, which is basically the energy level. And what you can see in here, as we talked about the couple of things of terminology, if you're asked a question, how many maximum electrons in the n equals 2 level are shell. Again, as we were talking about towards the end there, when you're asked that question, when they talk about a shell or they talk about a level, some books, depending on when it's written, what they're talking about is if you went to that energy level and you basically would count all the orbitals that are on that energy level. Now, since if we did, for example, n equals 2, On the second energy level, there's only s orbital and there's also the p subshell. So those are the only orbitals present. And since the p subshell has three individual orbitals and the s orbital has just one orbital and each could hold two, if we maximally filled up that level or shell, we would be able to put in there, as we talked about earlier, 8 total electrons if we filled the entire thing. And if you went to the third energy level and you want to know how many was in that level or shell, you would be taking all of these, right? And now at this point, we're going to be able to put 2 into the s orbital. We're still going to put another 6 into that p subshell. But because we're on the third energy level, we now have d orbitals available to us, right? And if we were able to fill the d orbitals, we could put another 10, which means when we get to the third energy level, if we completely filled that level or that shell, we're looking at 18 electrons if we completely max that out, that entire level, again with the extra 10 that's in there. So if you're asked that sort of question, how many in a level or shell, that's what it's referring to, the energy level, any orbital that basically has that number you want to count. A quick way that you could do that without having to maybe draw it and try to figure out, what's there is if you just want to know on a shell or a level, which basically is the same thing, and you want to know the max number of electrons. Now, mind you, if you get to like the 7th energy level, you wouldn't probably want to draw out all the little lines and try to figure out how many orbitals there are. You could figure it out by taking 2 times n squared. N is the n equals 1, n equals 2, the energy level. So you would square it and then times it by 2. So for example, the one we just did first, energy level is 2. You would take 2 squared times 2, that would be 4 times 2 is 8 electrons if you maxed it out. If you did the third energy level, you would square the 3 first and then times it by 2. That would give you 9 times 2, which is 18 electrons. So if you just want to know, hey, on this particular energy level, helpful to calculate it that way, just make sure you square the n value first and then times it by 2. Definitely if you get to the 7th energy level, you're looking at 49 times 2, right? A lot of electrons you could stick in there, technically speaking, is available to be put in there. And that technically would get you into some of those other orbitals that we never get into. But, it is sort of available at that point. Any questions on that there? The other terminology that we also talked about earlier, again, is if you're asked about a subshell or sublevel, we're talking about something like this. Again, a grouping of the same type of orbital on the same energy level where there's multiple orbitals. So Ds have 5 individual orbitals. If you're looking at the 4D subshell, that would be what this is referred to as the 4D subshell or sublevel, is all of those orbitals together, which once again, you could fill in there 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 electrons to max that out. Now, if I asked you how many electrons you could put in a 4p orbital, what would the answer be? That's the trick question. In any individual orbital, how many can you put? 2, right? So when we say a 4p orbital, it could only hold 2 electrons because it could be this one, it could be that one, or it could be that one that we're talking about. If I reworded the question and asked how many electrons in a 4p subshell, how many would that be? That would be 6 because the 4p subshell would be all of them together would have 6 electrons. So again, no matter what, if it just says orbital, how many electrons can you max it out? Doesn't matter what the letter is, choose the answer. If it's multiples, then it's going to be something worded like a subshell or sublevel. Any questions on that there? Now, before I scribbled all over this paper here, what we're looking at is, again, our energy level increasing as we go from the bottom. And this is what it looks like for hydrogen that actually has just 1 electron present. And what we see is as we have these energy levels box, everybody in the second energy level is exactly equal in energy. They're exactly at the same spot. Everybody on the third energy level is equal at the exact same spot. If you go to the fourth, same deal. But as you know, electrons are negatively charged. So what happens when we put a bunch of electrons together into an atom? Do they really want to be near each other? They don't, because they're negatively charged, but they can't escape because they have that kind of attraction, right, to the nucleus and stuff like that. So what happens when we get a lot of electrons in, more than one electron, is if you take a look at these energy levels, there's actually a shift that occurs in the actual energy of the orbitals. So before they were all perfectly lined up, and I'm going to get rid of the markings here so you can maybe see it better. So before, with one electron all perfectly lined up, but then when you go to the next one, now we get some separation in terms of energy. And this is, again, really important in terms of where the electrons end up. Once again, they do fill from lowest energy to highest. So we would always start at the bottom here at the 1s orbital. Then we would go to the 2s orbital, as you would imagine, the 2p orbital, 3s orbital, 3p orbital. Right here is where people screw up because they expect, logically, number wise, I did 1, I did 2, I'm on 3, I should probably go to 3 next. But because of what happens with this shift in energy, what actually happens in terms of the orbitals that are next lowest in energy is actually the 4s is actually lower in energy. Then you go to the 3D and then the 4p, and then you have that happen again. The 5s is lower in energy than the Ds. So because of the shifting in energy, when the electrons go into the atom, they're going to actually follow that order. So they do not go in terms of filling order, which is how we typically write electron configuration. They do not go exactly all the ones together, all the twos, all the threes, and stuff like that. There's this kind of separation that occurs. And obviously, as I mentioned, that is the way that we would fill. So how can you figure out the order without trying to remember it? This little chart here is a really good chart. And if you know this chart and you know the two things that we talked about earlier, which is if I fill up an s orbital, that's 2 electrons. If I fill up a p subshell, that is 6 electrons. If I fill up a d subshell, that's 10 electrons. And if I fill up an f subshell, that's 14 electrons. You will be able to write any electron configuration you would need to write by just following this chart. So let's talk about how this chart works. This chart works up here at top. This is where you start. And you basically follow, like, yes, you follow here and you would hit the 1s orbital. You would come to the end of the arrow. And then what you do is, if you need more, because you can only put 2 in that, right? You would come back and swing back around. And then you would come to your 2s orbital. And then if you needed more electrons, you would come back to your 2p, to your 3s next. Then you'd come back to your 3p. And here's your 4s. And again, you can just continue to follow, obviously, that pattern all the way around. So you always start at the top and you always keep going. You basically keep going until you run out of electrons. So when you run out of electrons, you're done and you can put your numbers. Now, you may be saying, do I have to remember this chart? It's very helpful. It is also a very easy chart to recreate for yourself on your paper. And all you have to remember is 1, 2, 3, and 4. And the things that we just talked about. And what I mean by that is on the first energy level, right? The only orbitals there are S's. So you just put a 1s. It's not until you get to the second energy level that you see P's. You go down to the right a little bit and put a 2p. On the third energy level, that is where we see the D's start. Down to the right a little bit, put a 3D. And lastly, on the fourth energy level, that is where we see our F start. Down to the right, put an F. At that point, if you remember 1, 2, 3, 4 and what orbitals start on those energy levels, all you simply have to do is underneath each of those numbers, just run them to 7, yeah, with the same letter down underneath. So this would be like 2s, 3s, 4s, 5s, 6s, 7s, 2p, 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 5f. And now you pretty much have recreated that chart for yourself on the paper by just remembering 1, 2, 3, 4, go diagonal, drop the numbers underneath them. And it's something you could create really, really easily. I'll be honest with you, if you can't remember where these numbers end, even if you laid up a 7D and like a 6F and 7F, even though we probably won't get there, you'll never get there. So well, even if you put the extra numbers there at the bottom, you won't ever get there to even screw up and use them and stuff like that. So, you know, obviously, like I said before, we typically don't need any of those. And even if you put some extra numbers at the end, it won't make a difference. So that's a really good thing. So again, if you know this chart and you know what's on the left there, 2, 6, 10, and 14, you're good to go in terms of electron configuration. Any questions on that? All right, so let's write some electron configuration and see how good we are. Here's a thing from your book, again, showing you that order of where things kind of go. All right, so electron configuration tells us the order in which electrons are in the atom. We write electron configuration, what is sometimes referred to as filling order, how they are kind of put into the atom. We don't typically, in any chemistry class, pretty much, write it based on energy. I only took one chemistry class ever that wrote it based on energy. Everybody writes it on filling order, which is what we're talking about in that chart that we just saw. Now, how do we know how many electrons somebody has? That's pretty straightforward as well, because we know that if we look at the periodic table, the atomic number is the number of protons, and if the atom is neutral, it will have an equal number of electrons, right? So if it doesn't have a charge, it's neutral. However many protons it has should be how many electrons it has. Obviously, if it has a charge, we'll talk about that at the end probably, but no charge, that's how we can figure it out. All right, so let's take a look at our first one, which is hydrogen. And once again, if we look at hydrogen on the periodic table, hydrogen is number 1. And number 1 means it has 1 proton, but more importantly, it would also have 1 electron. So here's our chart, and we're going to write our electron configuration. So once again, we always start here 100% of the time. We just always start there. We're going to roll this way, and the very first orbital we hit is on that first energy level, and it would be referred to as 1s1. Once again, that would be the electron configuration for our hydrogen. The first number is the n number, or the energy level, the principal quantum number. So that first big 1 represents that we're on the first energy level. The s represents that my electron's hanging out in the s room, basically, or s orbital. And the 1 that's on top, which is a superscript, is the number of electrons in an orbital or subshell. Now, that is how you say electron configuration 1s1. The first number should be a regular number, lowercase letter. Superscript up on top should be the number that's on top. There's no commas, no dashes, nothing like that. So that's how it should look. There is another way that we write electron configuration. Don't fancy it up. It'll just make it wrong. Is we could represent it by what is known as orbital. I'm just going to rewrite it up here on top because I think it's easier to see in this room probably. Orbital diagram. Kind of follow your notes, and on your notes you'll have some boxes, I think. Now, the orbital diagram either uses boxes or lines to represent the individual orbitals, and we use arrows to represent the electrons. So if we were here with this electron configuration for hydrogen, we would have 1 box or 1 line, and that would represent the 1s orbital. And because it only has 1 electron, we would put in the box 1 electron. And when you put the arrow into the orbital, the first arrow always points upwards. It is what is referred to as having a spin quantum number of +1/2. Basically means the arrow is kind of pointing up. So electrons have their own sort of spin, and it's referred to as a positive half when it points upwards, and it always, the first one in always goes that way. That means, for example, at this point, how many more electrons could I put into that s orbital before it's filled? I can only put one more, right? And that happens at helium. So let's take a look at helium. Now, when we get to helium, we run into one of the first sort of rules about electron configuration, and that is, let's just talk about helium. Helium obviously has 2 electrons, as it's number 2 on the periodic table. So it's got 2 protons and 2 electrons. Now, we know if we look at our little chart, we're again going to start here, and we're going to roll into our 1s orbital. So our helium's electron configuration would be 1s2. 2 up on top. And again, the first number tells us we're still on the first energy level. We're still in the s orbital. And the number at the very, very top here tells us that orbital now has 2 electrons in it. Now, when we think about our orbital diagram, there is a rule that we have to follow, which is known as Pauli's exclusion rule. And if you think about how the electrons will go into that 1s orbital, here's your options, right? We have one going in the upwards direction. The other option is we could put it in the same direction. Or our other option is basically we could go one up and one down. Or I guess your third option is, if you didn't know the rules, you could put them both down, which wouldn't be good. So how does a second electron kind of go in there? Pauli's exclusion rule says that no 2 electrons that are hanging out in the same orbital can have the same 4 quantum numbers. Now, we're not going to really get deep into quantum numbers, and you will in the next class, but there are 4 quantum numbers. There is n, which, as we've talked about, the energy level or the principal quantum number. There is L, which is known as the angular quantum number. There is m sub L, with the magnetic quantum number, and there's m sub s, which is the spin quantum number. And again, you don't really have to worry too much about this because we're not going to be asking questions on particularly those. But I'm just going to use it to illustrate what this rule is and why we sort of end up with it. So I'm going to give you, when we look at an electron, maybe I'll put it here. Yeah, I'll go here. So if I take an electron in this 1s orbital, and we do know from our first conversation that the first one goes in the upwards direction, which clearly eliminates, obviously, that option, right? When we would assign, for example, quantum numbers, and you do not have to assign them in this particular class, probably when you go to 1a, you will. The energy level that this is on is 1, right? So n would equal 1 for that particular electron in that orientation. L could have values of 0 to n minus 1. So 1 minus 1 is 0. So the L value for that electron would be 0. By the way, just a preview, L value of 0 represents a s orbital, which tells us it's basically in the s orbital. That's basically what L tells you. It tells you what orbital it's in, the electron. Now, when you do m sub L, it could actually go from minus L to 0 to plus L. And in the case of this, 0 can only go to 0. That would be 0, which means it basically tells you how many orbitals there are. And since S only has 1, 0 is only one number, if we call it a number, and that's one orbital. That's the only S orbital possible. And the spin is which way that electron is going in that particular orbital, and it's pointing upwards. And as I mentioned before, that's what's referred to as having plus half spin. So those technically would be the 4 quantum numbers for the electron heading in that direction. Now, if I did it in this direction, with this second electron also pointing up, that second electron here would hit all the exact same numbers. which would violate Pauli's exclusion rule because basically it's the same exact spin and all that. So this cannot happen when you have two electrons. By the way, we won't go through the numbers here, but they're both pointing in the same direction and they're in the same box. They also would share the same four quantum numbers. So the way that we get around it is when the second electron comes in, it actually would be pointing in the downward direction. And now in terms of the quantum numbers for this red one, n is still 1. It is still in an s orbital, which means it's a value of 0. The m sub l is still 0. So right now we're 3 for 3 in terms of the same. But what makes the difference is the spin. And this orientation is known as minus a half. So because they are spinning opposites of each other in that orbital, they do not violate Pauli's exclusion rule because they do not have identical quantum numbers. This orientation is what is referred to when you have an electron going up and in the opposite direction as paired spin. They essentially cancel each other out. One's going plus a half, minus a half. Everything kind of sort of cancels out. So the short answer to what happens is when two orbitals go into one, or two electrons go into one orbital, the second electron goes downward. The first electron always goes up, second always goes down. They should always be pointing in opposite directions. They never should be pointing in the same direction. Any questions on that there? So that is basically what happens when we get to helium. So if we draw our orbital diagram for helium, we will still have one box for our 1s orbital. First electron goes in upwards. Second electron always goes in the downward direction there. At this point, can I put any more electrons into that orbital? I cannot. It is filled, right? It has 2. So now what would happen if we have more electrons is we would have to zig back around and come to there. And that happens at our next spot, which is lithium. And lithium is 3 on the periodic table. So it's got 3 electrons. So again, starting up here at the top, we're going to hit our 1s2. We now have to swing around and hit our 2s1. If you count up the top numbers, that's 2 and 1 equals 3 total electrons. We have now placed 3 electrons in the atom. Once again, there's no commas, no dashes. That's how you write it. Big 1, lowercase s, 2 on top. Big 2, lowercase s, 1 on top. Yeah. Why would it stop at 2s and not go to 2? Because remember, s is actually lower in energy than the p orbitals on the second energy level. So we always feel from lowest energy to highest. So the lowest you could get in any atom is the 1s. Then the next lowest is the 2s. So you cannot go past the 2s until it's filled to go to the next lowest. So it always feels from lowest, next lowest, next lowest. But you can't move from one orbital to the next until you fill the previous one. So it has to be filled before you move on. And that's why we can't just leapfrog like down here and go, hey, let's just go there. Because this guy is the lowest and we can't move on from that until we fill it. Once we fill it, we have to go to the next lowest and fill it before we can swing back around and kind of get into the next set of orbitals. And that's based on that one when we flipped the slides and they weren't all equal anymore. So some orbitals were lower in energy than others. So that always goes in that direction. Other questions? At this point, I have how many electrons on the first energy level? I have 2 electrons on the first energy level, right? On the second energy level, I have 1 electron on the second energy level, right? So that third electron is higher in energy than those other 2. It's further away from the nucleus than the guys in the 1s. Now, if we were going to do our orbital diagram for lithium, we would need a box for our 1s, and we would need a box for our 2s orbitals. I'm going to draw it right to left because I'm going to run out of room. But technically speaking, energy increases this way. You would technically draw the 1s there and then the 2s above it in terms of energy. But for all these, I'm going to run out of room. So I'm just going to go sideways and not draw it correctly in terms of energy, but just draw them together. Once again, first electron goes in upwards. Next electron goes in downward. We're now to our next orbital where the first electron goes in the upwards direction, and that would represent our orbital diagram at this point. You could also hopefully visually see that you only have room for one more electron in that 2s orbital before you would then have to move on to the next lowest set of orbitals, which would be the 2p. So we can fill that next one up with our next one on the periodic table there, which is number 4, which is beryllium. And if we take a look at beryllium, beryllium is number 4, so it's got 4 electrons. Once again, we're going to start up here. We're going to roll into our 1s2. That is now filled. We're going to zigzag back and do a 2s2. So 1s2, 2s2. Again, if you count up the top numbers, we now have a total of 4 electrons. We have now 2 electrons on the first energy level and 2 on the second energy level, right? So on the first energy level, they're hanging out in the s orbital. On the second energy level, they're hanging out also in the s orbital. If we were to do our orbital diagram, once again, we would need a 1s box and a 2s box. Again, not drawn correctly in energy, but we're just going to go this way. 1 up, 1 down, 1 up. We still follow Pauli's exclusion rule and has to put for our 2s it going down as well. We have now paired off the spins. There is no more room there in the 2s orbital. We have to follow our chart. If we have any more electrons, we need to now start filling up the next lowest energy level orbitals, which are the 2p. And at this point, we're now going to hit a 2p subshell, right? So on every level, there's a 2p subshell, which means how many individual p orbitals should there be on that subshell? There's going to be 3, right? So now we're opening up an opportunity to fill the next 6 electrons, right, before we have to move on. Again, with the s's, there's only 1 orbital. So let's continue on here. We're going boron next, which is 5. So boron is 5 electrons. Once again, starting up here, we're going to come to our 1s2. We're going to zigzag 2s2. We're going to zigzag. This is going to be a 2p1 in this case. At this point, how many electrons do I have on the second energy level? What do you think? What number up there shows you the energy levels? It is the front number, right? So that's the first energy level. This is the second, and that's the second. So on the second energy level, I have a grand total of 3 electrons. On the second energy level, right, again, if you think about it like a hotel and the energy levels are different floors, on the first energy level, we only have an option of 1 room on that floor, and that's the S to put electrons in. On the second floor, we have options of 2 rooms. We can have an S room to put electrons in and a P room to put the electrons in. And in this case, we got 2 hanging out there in the S room, and we got 1 hanging out over there in the P room at this point. If we were going to do our orbital diagram for boron, we will again need a 1s orbital box, a 2s orbital box. But now when we get to our 2p, because it is a subshell, we need a box for each of the individual p orbitals. This basically represents that px box, py, and pz orbital that we saw that was flying around on the different sides and stuff like that. So when we fill this, and obviously just like before, if you drew it correctly in terms of energy, 2s would be above the 1s and the 2p would be above, obviously, the 2s. We will fill like normal, up and down. Now we're completely filled. Up and down, we are completely filled. Now, what happens when we get to a subshell that has multiple orbitals? In terms of the orbital diagram, we always fill it left to right. So we're going to put our very first electron right there in that orbital on the left. That's really the px orbital that's going to get the first electron, again, in the upwards position. So always the first electron that goes in, always in the upwards position. At this point, we could put how many more electrons in that subshell before it's filled? We could put 5 more before it's filled, right? So let's continue on. And let's talk about another sort of important rule that sort of happens. And that rule is what is known as Hund's rule. And Hund's rule basically says that the most stable arrangement for electrons in a subshell is the one that creates the most parallel spins. So we talked about a second ago that if we put electrons in like so, that is what is referred to as paired spin. Parallel spin is where electrons are heading in the same direction. So they're in the same direction, gives you parallel spin. So why is that an issue? So let's go and look at the one that we'll come across, which is carbon. Carbon is 6 electrons. Once again, starting up here, we're going to go our 1s2. We're going to zigzag back. We're going to go 2s2. We're going to zigzag back and go 2p2. Once again, if you count up all the top numbers, that is 2, 4, 6 electrons we put into the atom. Now, when we get to our orbital diagram for carbon, we again will have our 1s box, we'll have our 2s orbital, and we'll have our 3 boxes that represent our 2p subshell. They're going to fill like so, up, down, up, down, up. Now, where do we put our next electron? Again, the option is basically we could put our next electron there. Or the other option is we could lay up our next electron like so in the next orbital. Now, we follow Hund's rule, which says we want to maximize parallel spin. The first one on the left there is paired spin. That's not maximizing parallel spin. So based on Hund's rule, we would not kind of fill up the orbital one at a time, but we actually will put our electrons in the same direction in the next over orbital. So the next orbital will get 1 electron. And that's what happens when you hit any subshell that has multiple orbitals. They feel like so. Maybe you saw me do this earlier and wondering why I was doing it like this. They fill one at a time until all of them are filled. And once they're all filled, the next thing you would do is go back to the other side and start pairing them up. And what that does by putting 1 electron in each individual orbital, it follows Hund's rule, maximizes that parallel spin, and then by pairing them up left to right, you're still maximizing the parallel spin. So that's how they go in to a subshell where there's multiple orbitals, one at a time, all pointing upwards. When you run out of orbitals, you go back and then start pairing up if necessary. That means our next electron, which happens at nitrogen, should end up at the orbital on the right. Yeah, so let's take a look at that. So that's nitrogen, which is number 7. And again, starting here, 1s2, zigzagging back, 2s2, zigzagging back. And now we're at 2p3 at this point. Once again, looking at our orbital diagram, we'll have our 1s box, 2s box, and again, our 3 boxes for our 2p. We're going to go up, down, filled, up, down, filled, maximizing parallel spin. We're going to put electrons into each of the orbitals individually, all pointing upwards, again, maximizing that parallel spin. At this point, if we have 1 more electron, we have no choice but to start going back and pairing everybody up. So singly in first, then back to parallel. Any questions on that there? Why don't we finish the first 10 here since we're halfway, almost more than halfway. Let's hit oxygen next. So oxygen is 8 electrons. Once again, following our normal path. We're going to go 1s2, 2s2, 2p4. Looking at our orbital diagram, our 1s, 2s, 2p, up and down field, up and down field. We're going to go up, up, up. Now we come back over here to what is really the px orbital, and now we're going to start pairing them up. Again, we still have 2 unpaired electrons, which keeps that maximum sort of parallel spin. As you could also see visually, we're 2 more electrons to filling the 2p subshell and having to move on. So let's finish up those last 2, which is fluorine next, which is 9. I'll steal it here. Looks good. Fluorine is 9 electrons, so we got our 1s2. We're going to zigzag 2s2, zigzag here, 2p5, I think, right? At this point, how many electrons do I have on the second energy level? I have 7 on the second energy level, 2 there and 5 there. In this case, we got 2 electrons hanging out in the s, and we got 5 electrons hanging out in the p orbitals on that second energy level. As we did earlier, right, to max out that energy level, you have to have 8, right, which is why we have 1 more spot to go before we max it out. And our diagram here, 1s, 2s, and our 2p. So up, down, up, down, up, 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 down, down. And again, there is our last spot there for a place to put an electron. And that happens at our good friend neon, which is number 10 on the periodic table. And let's take a look at that. So neon is 10. And again, same pattern. Always started up on top. 1s2, 2s2 as we zig back around. And now we're going to be at 2p6. At this point, we now have 8 electrons on the second energy level, 2 electrons hanging out here, 6 electrons hanging out here. We still have 2 electrons on the first energy level, obviously, along the way. So looking at our orbital diagram, we're going to go up, down, up, down, up, 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 and come back, and we are fully paired off. Now at this point, if I have more electrons, I am now forced to go to the next lowest, which would take me to the 3s orbital next to fill up. So again, as you can see, we always start at the bottom and we keep filling until we run out of electrons to fill. And that may completely fill the subshell, may not completely fill the subshell or orbital, but we keep going that way. Question on how to write electron configuration or orbital diagram. Okay. All right, so I kind of skipped ahead here and find where we're at here. Why don't you write, why don't you do it for argon? Why don't you write the electron configuration for argon there, which is 18. Look, so once again, we're going to start here on top like we did with all the other ones. So still going to take us to obviously our 1s2. That will fill that up. We will then go to our 2s2. Again, if you're not sure how many electrons you've added so far, just count the top numbers. We're at 4 electrons. We still have 14 more electrons to put in there. That's going to require us to zigzag back here to our 2p subshell. And we know we could fill the 2p subshell with 6 electrons as we just did. And that's going to give us now 10 electrons. We still got 8 more to go. That's going to require us to head down to the 3s because that's a 3s orbital. It could only hold a maximum of 2 electrons. We are now, if we count up the top numbers, 2, 2, 6 is 10, and 2 more is 12. That's then going to require us to zigzag back around, and we're going to hit our 3p subshell, which could hold a maximum of 6. and that should get us to 18 electrons. So once again, 1s2, 2s2, 2p6, 3s2, 3p6. Clearly, if you're going to draw your orbital diagram, you would need obviously the appropriate boxes for all that. And again, not going to draw it energy correct, but just kind of sideways here. And then we would have a 3s box and a 3p box. And at this point, everything would be filled, going in there, coming back and backing it up, filled upwards, 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 down, down, and down at this point. First off, any questions on the electron configuration there? So now let's say, for example, we went over to potassium. Now, potassium is 19, right? Electrons. And we know, obviously, argon was 18. So we would need to continue down to remember that after our 3p, we are now going to hit our 4s orbital. So argon's I'm sorry, not argon, potassium's configuration would be 1s2, 2s2, 2p6, 3s2, 3p6, and now 4s1, right, to get us to 19 electrons. At this point, we have how many electrons on the fourth energy level? 1. On the third, we have at this point, we have 8, right? 6 and 2. And obviously on the second, we have 8 at this point, and we have 2 on the very lowest energy level. Now, this is obviously potassium's configuration, but if we look at what we just wrote previously for argon here, which is 1s2, 2s2, 2p6, 3s2, 3p6, we do see that configuration obviously hidden in, not really hidden, but there in potassium's configuration. So there is a shorthand that you could do for electron configuration. And because really what I highlighted there in yellow is argon's configuration, you could write potassium's configuration as argon 4s1. And basically what the argon represents is, with the little brackets, it basically tells the person argon's configuration and then add whatever's to the right onto it, basically 4s1. So it's like a shorthand to do that. Now, argon, when we look at the periodic table, is a specific type of element. Argon is what element? It is the noble gases, right? And when you do the shorthand for electron configuration, it always has to be a noble gas that goes in the brackets. And it's the noble gas on the periodic table that comes right before whatever you're writing. So whatever noble gas comes right before whatever you're writing is what has to go in that bracket. Sometimes it's referred to as noble gas configuration, sometimes is that shorthand, but it always has to be noble gas. So again, if I was doing calcium, for example, which is 20, I know, okay, argon is 18, and then I know potassium was 4s1, and it's right next door, so it would be argon 4s2. Now, if we back up to, say, sodium, which is 11 on the periodic table, sodium on the periodic table is 11. I know if I go on the periodic table before sodium, I find neon hanging out there, right, in the noble gas before sodium. And I would actually put neon in the brackets and then continue on with the electron configuration, which is 10, by the way, right, for neon. So that is basically 2, 4, and 10. That means the rest of it has to start there, right, at 3s. And this would be 3s1 in this case. So it always has to be that noble gas in the brackets. It always should be the noble gas that comes right before whatever you're going to write the electron configuration for. Any questions on that there? Honestly, if you had neon's configuration, or you had to write the electron configuration for neon, you could just lay up neon in a bracket technically. I don't know if your teachers would be happy if you did that all the time, but technically that would be neon's configuration in shorthand, basically, is just a bracket around it. Any questions on sort of the shorthand move there? Yeah. That's what we just talked about there. Now, another principle that's sometimes talked about in terms of electron configuration is what's known as the off-ball principle. It doesn't have too much to worry about in terms of electron configuration, but it basically says that just like protons that are added to the atom one at a time, we add electrons the same way. So we add them one at a time, lowest energy level to the next lowest to the next level. It has really no impact on too much of what's going on. There's our kind of shorthand we just talked about there. All right, we're going to finish up here talking about just transition metals in the last minute or so. Transition metals are obviously between group 2 and 3 that we talked about. And there are a couple, well, there's a lot of exceptions actually in the transition metal region, but there are 2 exceptions that you'll be responsible for. And by exceptions, what I mean is if you follow the little zigzag chart that we made, if you get to chromium, which is 24, and copper, which is 29, if you were to kind of follow the zigzag pattern, you would end up with, I don't think I have it here, oops. You will end up with 1s2, 2s2, 2p6, 3s2, 3p6. Remember at this point, 4s gets in there first before you get to the D, which would then be 3D4. So if you just follow kind of the zigzag pattern we did and you wrote it for chromium, you would get that. By the way, if you took it all the way from here, that is how many electrons I just boxed? 18. As we know, 18 is argon. So we could shorten that down to argon 4s2 3d4 as sort of a shorthand. Now, if you did that for copper, it would look similar. If you followed the zigzag, you would end up with argon 4s2 3d9. Now, it's been found experimentally that these two, there's actually more, but we just talk about these two, are actually more stable with one more electron in the d orbital and one less electron in the s. So the exception is actually like that. One of those electrons are actually up there. So the correct configuration for chromium would be argon 4s1 3d5. And the correct one for copper would be argon, also 4s1 3d10. And these are the exceptions that you should know for chromium and copper. Now, you may be asking, how can that happen? There's a few things that occur, which is the 4s orbitals are lower in energy than the 3d orbitals. So when electrons actually go into the atom, they do fill up the 4s first, and then they start filling up the d orbitals. They are super close in energy. And what actually happens, as we'll talk about next time, is when you actually start filling the d orbitals, they actually switch in energy. The d orbitals actually get lower in energy and the s's actually get higher once you start filling the d orbitals. That's how close in energy they are. They're kind of flip-flop in terms of energy. But it doesn't take a lot of energy to move that electron like up there because they're so close to energy, to each other in energy. What that does in terms of stability, if you think about it, is we just really maximize a lot of parallel spin there, right? By doing that. So we maximize a lot of parallel spin. Hund's rule makes it more stable. And it's the same sort of exception here. We kind of fill up the d orbital and maximize the s orbital with parallel spin because after they flip, the S is actually higher. So now we got that parallel spin at a higher energy level, and it sort of makes it a lot more stable. So for us, chromium, copper, the 2 exceptions you need to know. And the exception basically is one more electron in the D, one less electron in the S. And truth be told, if you look on the periodic table where chromium and copper are, and you go down and in, things like silver, things like PD, that there's similar exceptions that happen. If you look at PD, it actually has no electrons in the S. They've all went up to, they've all been promoted up there to the D and stuff like that. So there's a lot more exceptions kind of under chromium, copper, and in on the periodic table. But for our class, you'll just be responsible for chromium and copper. Everybody else, you could just write the electron configuration from that chart, just know that if you're in that area, you're probably writing technically the incorrect one based on stability. All right, we will lay it up there